Okay, let us begin. All right, so last time we talked about uh, Rangutta method, right? So we talk about Rangutta method of order 2, right? And then we see that it is basically about determining the coefficients alpha, beta, b1, b2, right? So in that standard formula, and then we see that we can determine the coefficient such that the truncation error of the method when original solution y of t is substituted is equivalent to order of h3, right? So we do the computation in such a way that the order is h3, right? So for the truncation error at by t, right? So that is what we did there. So then by using that we can graphically interpret this, right? So basically what you do is you have a slope L1 at y of t, and obviously that is y prime. So then that is f of t comma y. And then what you do is you go t plus h there, right? So it has to be t plus h, sorry. Right, so you when you go t plus h, then you take that point, right? So f of this and this, and obviously that gives you the other slope, and then L3 and L4 are basically the averages of those slopes. So that is why, that is how we develop the Rangutta method from Taylor's expansion, because you know that in Taylor's expansion what we did is we just approximate the derivatives, right, in terms of right hand side function, right? So here in Rangutta method we basically interpret it with an average function, or approximate it with an average function, right? So right, so then told you earlier, we wrote down that there are certain famous choices for B1, right? So eventually we see that your Rangutta method depends on what are the values you choose for B1, right? So basically all the other components, alpha, beta, and B2 are depending on B1, right? So you know that. So then it is all depends on B1, and depending on the choice you have for B1, you will have different types of Rangutta methods, and we see that there are certain numbers which are more favorite for the choices that are half, 1/4, and half, 3/4, and 1. So now let us see an example of such a method, right? And then we will talk about the general approach. Okay, so when you substitute b is equal to half, right? So you see that you get the Rangutta method, right, as yn plus 1 is equal to yn plus h over 2, right? And then fn and fn comma yn plus h time fn this, right? So this is how you get a second order Rangutta method, right? So this has a special name also, right? Okay, so this is also called as Heun's method. right? Okay, so now note that okay, so this is just observation. Okay, so you can see that in this method, right? So this term, in this term, particularly this part is yn plus h times f of tn comma yn. Right? So this is obviously, you know, the right hand side of your Euler's method. Right? Explicit Euler's method gives you yn plus 1 if you evaluate that. Right? So that is what I wrote here. So that is Euler's method. So that, in a sense, you can see that. So Tn plus h is basically Tn plus 1. You all know that because that is how you choose h, right? So h is the step length. So Tn plus h is basically Tn plus 1. And this one is basically yn plus 1, right? So you know that. Right? So f, you know, is y prime, right? So eventually you can say that this is the approximation, right? So this term is basically, you can see that is an approximation of the original solution y, right? Derivative of the original solution y, that is y prime. It is an approximation for y prime at Tn plus 1, right? So eventually this term, you know, is basically an approximation for y prime at Tn plus 1. Right? So that is the interpretation of this equation, right? So you can easily see that, right? So eventually, if you see that is the interpretation of this, then now you look at this. That is why we call this as an average slope, right? So you see that you have this, right? So f of Tn comma yn plus f of Tn plus h comma yn plus h times f of Tn comma yn, right? So you have this right here, right? So now this is the part we are looking for, right? And then I put an 1/2 in front, right? H is always fixed, so I take this part only and I try to interpret what this means, right? So clearly this is an approximation for y prime at Tn, right? So you know that, right? That is obvious. And by this argument or this explanation, right, now you know that this is an approximation of y prime at Tn plus 1. Okay. So that is the approximation of y prime at Tn plus 1. So basically what you have is this is half. Right? So this basically approximately this. And this half of this is basically approximately this. But this, you know, is the slope. This is the slope at Tn, right? I should write properly. Right, slope at Tn. And this is basically right, Tn plus 1, slope at Tn plus 1. Right, so then basically what you do is you add them together and divide by 2. Right, so that is what you did. So slope at Tn and slope at Tn plus 1 divided by 2. So basically that is the average slope over Tn plus 1 and Tn and Tn plus 1. Right, so this is basically, right, this is equal to okay, so this is basically an average slope, right, over Tn comma Tn plus 1. So that is why we keep on saying that in Ranguta method we kind of have an average slope, right? So that is why. So now you know this is the basically the capital F, right? So you have capital F T of T n comma yn and h, right? So this is what your capital F is, right? So that is capital F at T comma y of T with h, right? Right, so by this example, you can obviously see that capital F, the function you have on Ranguta method, right, is basically an average slope over the interval t comma t plus a. Right, so that is why you have the Ranguta method. Okay, so now I will give you another example, right? Just by putting b1 is equal to 1, right, you get another method. I'm sorry, b2, no? We keep on saying b2. Okay, so if you put b2 is equal to 1, then you have yn plus 1 is equal to yn plus h times f of tn plus half h, comma yn plus half h, comma f of tn yn. Right, so that is in a way a different way of forming the average, right? So this is the standard way of average. You know, start point plus end point divided by 4 is basically the regular average, right? So the proper meaning of average, right? So that in a way is a different average, right? So here you can see that this point is somewhere in the middle of Tn plus 1, right? So this point is basically Tn plus Tn plus 1 over 2. So here your average is basically about, right? So the average is basically about the point, the middle point between T and Tn plus 1. So in that point, you are talking about a certain kind of a slope, right? So eventually it is a slope and it has some kind of a concept of average of slopes, but here it is obvious that it is the proper average, but here it is not the average. So here you basically go for the average over the points T1 and Tn plus 1, right? So that is a different way of average. And if you put 3/4, you can see it forms another form of average, right? So that is how this Ranguta method is developed, right? Basically, it's all about kind of an averaging the slopes, right? So that is why we choose this very simple Ranguta method and try to explain Ranguta method based on these, right? So now what we are going to do is we are going to look for the general framework. It's how we can generally formulate a Ranguta method. So this is a special case, two-step method, order two method, right? So then you know it is yn and yn plus 1. So it's quite simple. But in general, you don't need to have it as a second order method. You can have higher order also. So let us focus on a general formula for that. Okay, so we are going to talk about explicit Ranguta method, a general framework. So basically, we develop a higher order method, right? So Okay, so in this second order method, you can see that, right? So even when you put b2 is equal to 1, and so you see that obviously in general you will have tn and then the next point is tn plus 1. But here you can see that you go to some intermediate point between tn and tn plus 1, right? And then you do some evaluation around that, right? So in that way you are evaluating, right? And in general, this is different from Euler method, right? So this has a slightly different formula. And similarly, you can change things. So that is why what they do is they start with yn, right? And then evaluate at the next step, right? So this looks more like a Euler method, right? So when you put this equal to 1, and if you put a21 is equal to 1, then z2 become the Euler method, right? So yn plus 1 according to Euler method, right? So it is kind of an extension of that with all generalized formulas, right? So these can be any numbers. Aij's are coefficients of a certain matrix or components of certain matrices. They can be numbers which can be evaluated or which can be uh, assigned certain values, right? And then this z1 depending on your previous choices. So it's basically creating a convolution of functions, and eventually you will have a uh, kind of an again and again. It is basically average for approximations, right? So that is how we are developing, right? So based on these notations, you can define the Rank-Kutta method as follows. Right, so basically these you can think of as derivative for approximations, right? So this is a approximation, this is an approximation, this is an approximation at certain points, right? So that's how we are doing. Okay, so this is how we define the Rank-Kutta method in general, right? So these are coefficients Aij's, Bj's, Ci's are given, right? And the way the coefficients are given define different type of numerical methods or different types of Ranguta methods, right? So in general, this is how we define the Ranguta method, right? So basically, this is again, you can think as average function, right, approximates the derivative or the slope, right? So that is how we do that, right? So now we try to simplify this in a simplified form, right? So because writing this lengthy form is, but this is how in real, but writing this in a lengthy form is difficult in terms of computation. So let us try to write down it in a more simplified form, right? So Okay, so now you see that you can summarize this in a summation form, right? This is some yn plus 1 is equal to yn plus h times summation of bj, right? F of tn comma tn plus cjh comma zj, right? Running from 1 to s, and then all the zj's by the previous set of formulas, you can summarize this as this, right? So eventually a combination of these two together give you a general Ranguta method, right? Explicit method. So again, these there are a lot of coefficients, right? C naught, C1, C2, sorry, C1, C2, C3 up to Cs, and then B1, B2 up to Bs, right? And at the same time, Aij's, right? Basically, they form a lower triangular matrix, right? Strictly lower triangular matrix, I believe, right? And then C1 is 0. So a lot of things are there. So this is how they summarize this in a table, right? So they will always put this table, and if you see this table, right, without any notation, just give you 0, 1, and then there is 1, and there is 1, 2, things like that, then you know these are the coefficients, right? So the terms on this column, right, are C's, and then the terms on the bottom row is B's, and then the other terms within that part covered between that, right, are the coefficients Aij's, right? In general, right, usually the way the coefficients Aij's are chosen so that, right, for every row, the sum of those Aij's is equal to the C1, right? Say, for example, if this C3 is 1, this and this added together will give you 1. If this one is 5, all these numbers are chosen so that they added together and give you C, right? So these are kind of a usual notations and usual practice which people use in Ranguta method, right? So these are the standard forms we will follow in our lectures, right? So this is how we are going to do the Ranguta method in future, right? So I'm going to stop here because in the next class I'm going to start giving you an example of a Ranguta method in this form and try to develop certain things, right? So we will start with the example of Ranguta method in tomorrow's class, and then we will start talking about computations as well as convergence of the Ranguta method, right? So we will stop here and then continue the rest on Tuesday class, right?